Hello everyone, this is Sarbajit Dutta and welcome back to Educathea. In our last lecture, we have understood why quantum mechanics is so elusive in nature. We have also tried to understand the true nature of light, what light actually is and why does light exhibit so beautiful natural phenomena. We came to know that there existed a prevalent debate in the scientific community back in the 17th century to explain whether light is a particle or light is a wave. It was Sir Isaac Newton who proposed that light is made up of particles called corpuscles, and it was Christian Huygens who actually told the community that, light can also be a wave. We also know that Isaac Newton had great respect and repute at that point of time. So the scientific community was more inclined towards believing that, light is made up of particles and light is not a wave. But then something happened in the year 1801. Thomas Young, a British polymath who was equally capable in physics, physiology, music, literature, Egyptology, conducted an experiment which kind of suggested that, it's better if we treat light as a wave. What is that experiment? Let's try to understand it. So Thomas Young conducted an experiment in the year 1801, which is called the Young's double slit experiment, which kind of settled the debate between Newton and Huygens, and truly showed that, it's better if we treat light as a wave. What he did is as follows. He passed monochromatic light through two slits, S1 and S2. Light after passing through these two slits fell on a screen here. What he obtained on the screen was quite amazing. He obtained these alternate patches of bright and dark regions. Now this is very difficult to explain with the help of particle theory because, if light is made up of particles, the corpuscles, that is the light particles, will only pass through these two openings, S1 and S2, the two slits. And so we will get only two patches of bright regions on the screen corresponding to each of the slits. We will never get to see these alternate patches of bright and dark regions if light is made up of particles, because the light particles can never possibly pass through these barriers. This shows that the particle theory of light is kind of problematic here. You'll be surprised to know that with the help of wave theory of light, you can exactly explain this beautiful experiment. Let us try to understand how you can do it qualitatively. For that, let us take the help of thought bubble. Consider a tank full of water with a tap above it. You open the tap such that water falls drop by drop. What do you see? You see ripples, which are nothing but waves in water. Now the graph there shows you the water level with respect to distance from the tap, which oscillates. Here is the view from the side, which kind of makes it more clear. Now let's do the same thing with two taps. When you open both of them, the waves due to each of the taps overlap or add up. This is called superposition in science. The graph below shows you yet again the variation of water level with respect to position, which oscillates uniformly. Now let's see what happens if we have a sound source instead. We know that sound is a wave too, right? So even it must superimpose. If we play a sound source, it too creates waves around itself. It is pressure here which oscillates with respect to position, if we analyze the situation graphically. Again, if we have two sound sources, then superposition takes place. The waves due to each of the sound sources overlap. The graph shows the variation in pressure which oscillates uniformly now. Finally, let us see what happens if we have a light source. If you think of light as a wave, then even here we have wave formation all around. The waves fall on a screen where we get a uniform illumination. If there are two light sources, the same thing happens. The waves combine and we get alternate bright and dark patches on the screen. We will come to know later that light has some electric field component within it. So now it is the electric field which oscillates uniformly in this case. Let us now go back to our example of the water tank and see what happens if we keep a single slit as an obstruction in front of our water source. We find that the waves pass through the slit and whirl around. The water level versus position graph is a uniform oscillating figure. Now if you have two slits instead of one, then the same thing happens through each of the slits. Just the amplitude and the frequency of the two waves coming from the two slits are the same. This may not have been the case when we had two taps, because waves here reach the slits at the same time and with equal pressure. If we had two taps, it would have been difficult to open both of them right at the same instant of time and with the same water pressure level. As a result, there is no reason to believe that the amplitude and frequency would always be the same. These two waves with same amplitude and frequency combine together. This is a special kind of superposition because the amplitude and the frequency are always the same. This is called interference. We can also see it graphically here. If there are no barriers, then the water simply flows with a uniform variation in water level. The same thing happens with sound waves. A single slit placed in front of the source forces the waves to bulge out. The graph makes the situation easier to analyze. When there are two slits, then interference happens. The graph here is exactly similar to the water tank example. If we had no slit, then sound waves move freely with uniform variation. What happens to light waves is essentially interesting here. Needless to say that light does the same thing when a single slit is placed in front of the source. There is a small patch of illumination at the center of the screen which kind of fades away on the sides. A graphical analysis is shown here. Notice that the intensity on the screen is maximum at the center and almost zero at the sides. If we have two slits, the waves due to each of the two slits interfere and we get alternate dark and bright patches. This is also similar to the case where we had two light sources. Just here again, the amplitude and the frequency of the waves which are coming out of the slits are the same. The electric field variation and intensity curve are also given here. Notice how the intensity curve has changed. If we now remove the slits, then light travels freely. There is a constant illumination on the screen and uniform graphical variation of electric field. The intensity is just a constant function. All of this can in no way be explained by the particle theory of light. Never, ever, ever.
Now that we understand Young's double slit experiment qualitatively, let us also try to understand it quantitatively. For that, I would like to use the blackboard. So Billy, can you lend me the blackboard, please?
Thank you, Billy. So, from our previous high school physics classes, we already know what are waves, right? So, a wave is a disturbance. So, it is a disturbance which propagates through space and time. So these two words, space and time, they are of utmost importance here. So it's not just space, it's not just time, it's both space and time. We also know that a wave is usually drawn in this particular fashion. So you have the y-axis and the x-axis, and then a wave looks something like this. This particular curve has a special name. It's called the sinusoidal curve. The sinusoidal curve, because this resembles the sine curve or the cosine curve. The x-axis in case of a wave is always calibrated in either position or time, and the y-axis is some random function y which varies from case to case. So remember, in our examples, we always had a physical quantity which had a graphical variation like this. In our water tank example, it was water level which had a sinusoidal variation. In case of sound, it was pressure, and in case of light, it was electric field. So this y can be any random function which has a variation like this. Remember that if any physical quantity associated with anything has a variation like this, then you can call that thing a wave. We also know from our high school physics that a wave can be written in this particular fashion. Y is equal to a sine kx minus omega t plus delta, which is nothing but the equation of this sinusoidal curve. Here a is the amplitude, k is called the wave number and is given by 2 pi divided by lambda, where lambda is the wavelength of light. Omega is the angular frequency, and its relation with linear frequency or the normal frequency is just this, 2 pi f. The delta over here is called the epoch or the initial phase. So this is basically delta over here. If you had a graph like this is y and this is either x or t, and if you had a graph like this, then delta over here would have been 0. Next, we came to know what is called the superposition of waves. So if you have two or more waves, they add up together and you get something like this. Y is equal to y1 plus y2. So if there are two waves, a wave like this and a wave like this is y1 equal to a1 sine kx minus omega t plus delta 1, and this is y2 a2 sine kx minus omega t plus delta 2. Then the addition of the two waves will give you another wave like this, which is basically the addition of these two waves, and it will be nothing but y1 plus y2. This is called superposition of waves. An interesting thing to note about superposition is if you have two crests like this, and if they superimpose, you get a larger crest. So if this is a1, the amplitude, if this is a2, then the net amplitude is a1 plus a2. On the other hand, if you have a crest like this and a trough like this, then the net result after superimposition is something like this. So let's say this is a1 and this is a2, that is their amplitudes, and so this will be a1 minus a2. We have a special kind of superposition called interference. So if a1 and a2 are equal, and obviously k is same in both cases, omega is also same in both cases, then we get something called interference, which is a special kind of superposition. So if this is A and this is also A, then I'll get something which has a 2A amplitude. This is called constructive interference. And if you have a crest and a trough of equal amplitudes, and if they add up, you get nothing, which is nothing but destructive interference.
Now let us see how we can use all this to explain the Young's double slit experiment. So we have YDSE. YDSE is the abbreviation for Young's double slit experiment. The experiment goes in this particular fashion. We have a line source S and two slits in front of it, drawn in this particular fashion. So I'll call this S1 slit and this one S2 slit. So light waves come out from the source and they pass from both the slits in this particular fashion, and finally they fall on a screen here. What we get is alternate patches of dark and bright regions on this screen. I'll call the wave coming out from S1 as Y1 and the wave coming out from S2 as Y2. Now notice both Y1 and Y2 will have the same amplitudes because the wave coming from S hits both the slits at the same time and with the same pressure. So Y1 and Y2 will have the same amplitude. So Y1 can be written as A sine kx minus omega t plus delta 1 and Y2 as A sine kx minus omega t plus delta 2. Notice that the phase delta 1 and delta 2 are different for both the waves. Now, the wave which is hitting the screen will be the summation of both these two waves. So we'll have interference because the amplitudes are the same. So Y will be Y1 plus Y2. Now recall, we have a formula from trigonometry. Sin C plus sin D is given by twice sin C plus D by 2 into cosine C minus D by 2. We are going to use this formula. So we have twice of A as common, sin C plus D, that is the summation of these two angles. So we'll have kx minus omega t plus delta 1 plus delta 2 by 2, because we have by 2 here in the denominator, into cosine of delta 1 minus delta 2 divided by 2. So this is what we get. I can rewrite this as A sine kx minus omega t plus delta, where capital A is nothing but twice of small a into cosine delta 1 minus delta 2 divided by 2, and delta is nothing but delta 1 plus delta 2 by 2. Now we have destructive interference when a trough and a crest of equal amplitudes combine together, that is superposition takes place, and then we get a wave of zero amplitude. So if destructive interference was to take place, then this amplitude A has to be 0. So A will be 0 only if cos delta 1 minus delta 2 by 2 is 0, which will happen only if delta 1 minus delta 2 by 2 will be nothing but 2n plus 1 into pi by 2. That is odd integer multiples of pi by 2. Where n is nothing but 0, 1, 2, dot, dot, dot. Also recall that constructive interference was to take place when a crest and a crest of equal amplitudes combined, or a trough and a trough of equal amplitudes combined. And we used to get a crest or a trough, depending on the situation, of twice the amplitudes of the individual crests and troughs. So constructive interference will occur if A is twice of small a, which will only happen if cosine of delta 1 minus delta 2 by 2 is nothing but 1. This happens if delta 1 minus delta 2 by 2 is nothing but 2n pi, where again n is 0, 1, 2, and so on. So we see that if these two conditions are fulfilled, then constructive or destructive interference occurs. So when the waves from the two slits combine and fall on the screen, you have either constructive interference or destructive interference. The places where you have constructive interference, you get these bright spots. And the places where you have destructive interference, you get dark spots. So we can see how easily we can explain the Young's double slit experiment with the help of waves. And so it's probably true that light is actually a wave. The final nail to the coffin to the so-called particle theory of light was given by someone called Maxwell, who gave his famous Maxwell's equations. These equations not only showed that light is a wave, but also showed that light is a special type of wave called an electromagnetic wave. And this finally put an end to Newton's corpuscular theory of light. People were very sure that light has to be a wave. So if the 17th and the 18th century were dominated by Newton's corpuscular theory of light, the 19th century was all for Huygens' wave theory of light. But again, something else happened, which showed that, light can also be a particle. What is that? We'll see that again in our upcoming lecture. Thank you so much for watching this video. Do not forget to like, comment, and share this video with your friends as much as possible. And also don't forget to subscribe to the channel, because that would serve as a motivation for me to come up with more such beautiful videos. Also kindly press the bell icon over there so that you get a notification each time I upload a new video. Don't forget to check the description box down there for more updates, and have fun and enjoy science.